Okay, everyone, we're back. Welcome to CRCC webinar number 3. This is the final webinar in the series. Trevor Pope, Graham Saline, we're from the CRCC team. Trevor's the important guy. I'm just make a lot of noise. I'm the mouthpiece, and so let's step in and talk about today a lot about the CoderZ and the Cyber Robotics Coding Competition platform and how it works, so that you guys will be in a better position to support your students as they take part in the competition. So, webinar is going to last about 60 minutes, and we will answer questions at the end. You can see this link on the left here. At that link, you will find the links to the previous webinars, the slides, and in a couple of hours, the link to this webinar. We have to do this. We have to ask you to help us grow CRCC. The numbers are looking great. We want more people on the competition than ever before. So how can you help? Tell other teachers, get your whole school engaged, challenge your colleagues, share the experience. We're seeing people coming in at, like I said, at a great rate, but the more, the merrier. We can handle a lot more than what's in the competition right now. Use social media. CRCC for all. There's a lot of activity out there already. We're hoping that as soon as the competition starts, we'll see a lot more competition, a lot more activity on social media. This is the way for us to communicate with students and with you and with other teachers and with administrators and parents and so on and so forth. So put your experiences up, and without further ado, I am going to switch over and share the screen with my friend Trevor next to me, and Trevor will take us through the webinar.
Thanks, Graham. Good afternoon, everyone, and thank you for joining us today for this advanced training and coding webinar. My name is Trevor Pope, and my goal today is to provide information on scoring for each phase of the CRCC competition, to teach you to show you how to set up your InSchool Finals event, and provide coding training and support to ensure you are prepared with the knowledge and support materials available to manage your classrooms. I have a lot of material to cover this afternoon and want to share as many CoderZ missions with you as possible. So feel free to pose questions via the questions field. Graham and I will address these at the end of the webinar. Let's talk about state leaderboards for a minute. State leaderboards will be published this weekend. You can find links to the state leaderboards on the crcc.io webpage, as well as by logging into your teacher account and then clicking the scoreboard link on the left-hand side, the scoreboard icon. That'll bring you to this state leaderboard. It will look very similar to this link here. All of these links are going to be the live links for the leaderboard. Put your state name here. But again, all of these links will be published on the website and clickable links from your teacher field or teacher account in CoderZ. As I click that, I want to make sure you guys can see that on your screen. This is what we will be showing, what you will be seeing. Let me get the right phases here. So first off, we will have 3 phases of the competition. We have bootcamp phase, we have the competition phase, and we have the qualifiers. Ignore this inclusiveness phase. This is me playing with leaderboards here, but we'll have bootcamp, competition, and qualifiers. During bootcamp, what you're going to see is here's your school, the number of students in your school, the complete number of missions solved. This is the percentage of missions solved per your student. So this is a percentage of the total amount of missions available. You'll see a total score for all of your students combined in bootcamp, as well as a final score. This final score is calculated. It is your total score here multiplied by this percentage of missions solved. That's how we're going to get the total score. So here you're going to see the leaderboards in a school, a total score, as well as individual classes. So each individual class will be posted on the leaderboard here. We'll have an all category showing all classes, and then we'll have just individual classes as well as small classes. So this is really what we're going to be looking at as we move on, progress further in the event, is this small class. And again, this is looking at the same thing. Here it's going to have your school name, the individual class name, the number of students in your class, and the percentage of missions solved. So this is the total number of students and the percentage that that total number of students has solved. Ideally, we want this to be as high as possible. The total score for all students combined is going to be here, and then this is your final score. And again, this final score is this total score times this percent of mission solved to give you this final score. At the end of the competition, at the end of the boot camp phase, we are going to close the leaderboard, lock the leaderboard, and open up the competition phase. The competition leaderboard will start at 0 for every student, class, or school, and we will look for the same scoring criteria. We're going to look at the number of students in your class, the total class percentage of missions solved, and look at your total class score to get a final score, which is this total score multiplied by the percentage of missions solved. At the end of this competition phase, this leaderboard will be locked and the qualifiers phase will begin. The qualifiers leaderboards retains the student data collected during the competition phase. So all of your student data, all of your class data, and all of your school scores obtained in that competition stage will be retained and added to your qualifier stage scores. The qualifier challenges contain fewer missions, but they have a higher point structure. These missions will be more challenging, and each individual mission will be worth 300 points each. And your qualifier scores is added to your scores from the competition phase of CRCC and posted as a total cumulative score. For a final score here, this is what we're going to be looking at the end of that competition, or sorry, at the end of that qualifier stage. We're going to be looking at school total scores, as well as we're going to look at individual classes, total scores for your classes. And this is how we're going to get invitations to the finals. Based on classes, we're looking at two different aspects of classes. We're looking at a small class that has less than 20 students, so 19 or less, as well as a small class has 19 students or less, and a large class has got up to 35 students, for anywhere from 20 to 35 students. So these are the leaderboards that you'll see. Again, these will be listed on your state page. You can access those from your teacher account and from the CRCC.io webpage. InSchool Finals, let's talk about those for a second. InSchool Finals are a completely optional event and will be available to schools once the qualifier stage is completed. The school org admin can set the date and time for the event, and all students and classes compete together in this internal school-wide competition. The InSchool Finals are scored internally and will not affect the school status on a state leaderboard. So any scores obtained in this InSchool Finals will not be added to your state leaderboard. The school and classes scores at the end of qualifiers, the school and classes scores at the end of qualifiers, what was posted on the leaderboard at the end of qualifiers will be locked, and that's what's going to be used to determine invitations to the finals. You can use these in-school finals to create a fun school-wide activity to end the CRCC season for all students. You can use these in-school finals to determine the top students and the top classes in your schools, potentially hand out awards for the best student or the best classes. And you can also use these to select the students who will represent your school at the state finals based on these in-school finals results. Again, the in-school finals are an optional add-on to the CRCC competition. They're not required, and those ideas above are just recommendations. Each school can define if they want to hold an in-school finals and can determine how they want to use the results of those events. The in-school finals for all students are run for all students simultaneously. So set its time and date early so everyone in your school is able to compete. And the in-school finals will run for 2 hours. They will have a set number of missions for all students. Your org admin can set the in-school final. So your org admin will need to log into their org admin account. They will have an in-school finals checkbox, which will look like the screen, look like what you see on your screen here. Scheduling the time for the in-school finals is a simple matter of just selecting a start time and a start date. Uneditable fields are the time zone, which is based on your computer, and the duration, which is going to last 2 hours for everybody who participates in an in-school final. So again, the org admin is just choosing a start date and a start time, and then they hit the save button or next button, and you'll get a summary, which looks like this, of the in-school final. So here's the start time and date that you've chosen. start time, closing time, a duration of 2 hours, a show only timer feature, which is linked to this button here, as well as this URL. Now, the two most important pieces of information on this page are this show only timer button, and I'll give you more on that functionality in a minute, and this URL. This is a custom created link for your school-wide public leaderboard. Clicking this link brings you to a competition countdown timer. So as you click this link, immediately you'll get a screen that looks like this. So this will be your school leaderboard. It's going to have your school name here, as well as a countdown timer. It shows you what time or the countdown for when these school finals open. As this counts down to 0, your student screens will look like this. So the students will have access to CoderZ. This in-school finals set of missions or individual mission will become unlocked. The students will be able to click this, open the finals, perform the missions available to them, and then these will lock after that 2-hour window. The clickable link will bring you to these leaderboards. Here, this will say in-school finals. You'll have your total school information here. So it'll show your school, the total number of students participating, as well as admissions and school score for the internal finals. Here we'll show individual classes. So the number of classes you have registered. We'll have a list of classes here under this class name, the number of students and missions. So this is where you can find your class winner, or the class that performs best in your school, as well as there will be a students selection in this flyout arrow where you can see individual students and how well they're doing in this internal finals. You will also see a countdown timer on this upper right-hand side. This countdown timer starts at that 2 hours, and it's going to count down that 2 hours until that reaches 0. When that timer reaches 0, these leaderboards will lock, and schools will remain finals. So let's talk about my previous slide here. Remember this show-only timer that I talked about earlier? At any point when this competition is running, so say you've got 30 minutes left, 20 minutes left, the org admin can log in to their org admin account and click this show-only timer button. What's going to happen is it'll take away all of the information here on the leaderboards. That'll all be hidden, and everyone will see this. So you'll see your school. It'll show a timer ends in 1 hour and 50 minutes or whatever that time duration is, and it'll be a countdown timer to the end of that finals. The org admin can click this button at any time during the finals and repress those leaderboards. Student individual scores are still being calculated. However, this removes the leaderboards by not showing the class which performed best or the student champions. Can you say drama? Class or school winners will be can be publicly announced in a classroom or a school-wide ceremony, adding pomp and circumstance to the finals event. All right, let's talk CoderZ for a minute. CoderZ, again, is the platform we're using for CRCC. It's an online robotics learning environment that teaches robotic and STEM in a virtual cloud-based environment using gamified missions. It teaches the fields of coding, robotics, software, machine learning, as well as 21st century skills. As well as part of the CRCC, students are learning communication, teamwork, creativity, and innovation. With CoderZ, understanding of robotic systems and coding robots is super easy, and we assume no prior knowledge of CoderZ or coding for each student that participates, and there's no hardware, just a computer and a web browser is all you need to get going. The CoderZ software provides an online simulation of a rich environment with varied scenarios, obstacle courses, and a robot complete with sensors and outputs. On the right-hand side is the simulation window with gamified challenges. On the left-hand side are intuitive color-coded commands, as well as a visual editor using color-coded blocks. We also offer tips and help features in the CoderZ software. So essentially your students are never alone. There's always some resources to help them and guide them through the various tasks, various missions. Running the simulation is super easy. It's just a matter of clicking that play icon and watching your robot go, run the code that you've written. Let's see that again. That was exciting. Creating a program in CoderZ is easy and intuitive. It's just a matter of opening the menus on the left-hand side of the screen. These menus are all color-coded and easy to use. Choose one of the blocks in the menu, drag the block into the editing pane, and snap it to the previous blocks. And as you're ready to run your code, click that play button, click Run Simulation, and watch your robot go. All right, now let's code. I'm actually going to open up CoderZ. We'll do a couple of missions. I'm going to start with some basic navigation missions, showing you guys how to drive, how to make a pivot turn, how to make a curved turn. So we'll do some navigation missions, and then we'll get into the touch sensor using the object detection pack. We'll do a wait for touch sensor, wait for sensor. We'll do some smart blocks. We'll do some repeat loops, as well as learn about the gyro sensor. Sound exciting? So let me open up my CoderZ. You guys should be able to see this. Let me double check. Yeah, perfect. So I'm going to actually go into Bootcamp here and start with mission 1, which is Power Up. As I click on this mission to start the mission, it gives you kind of a little tip or a little overview as to what we're going to learn, what we're going to do in this mission. Do you know that you can? This is the first mission in Bootcamp, so we're going to start with basic navigation and then move forward into driving forward, driving backwards. We'll do some turns and some curves. And but here again, our first mission, just how to drive the robot. So here I'm going to click start. This is going to open up my CoderZ software. Again, let me make sure. Perfect, you guys can see this. All right, and as I open up the simulation, it does give me guided tutorials and walkthroughs as to what I need to do here. So here is the Power Up mission. Let's play with power. As I click next, my drive block has a power input that controls the robot drive speed. So here's the drive power block. Here's the speed I've got selected, as well as the direction. As I click next, we're going to run it. It's asking me to run this simulation, see how fast it goes, see what happens. So as I hit run here, you can see I'm moving fairly slow here. I get a pop-up that's got some snooze button. I'm going very, very slow. As I hit next, it says, okay, your power of 20 is too slow. Let's set the power to 100%, 100 maximum. So as I change that, the software recognizes that and say, try again. Let's run it again. As I run this, the simulation reloads, restarts itself, and now I'm going at a much faster speed, and I'm making progress. So there it is. Congratulations. I have written my first CoderZ code. Well, technically, it's not my first, but your students will have written their first code at this point. Hopefully, they're feeling good about it. They're feeling proud and are ready to move forward. So here, if I don't like the results that I got, I can hit this try again button. This will allow me to redo the same mission, rewrite code, tweak things, change things if I need to. I can go to the next activity, which will bring me, sequentially into the next activity that's next in our bootcamp series or next in the missions, or I can go back to the Learning Center. Now, most of the time, your students are going to click on this next activity, so they go right into the next mission and the next feature that we're teaching them. I'm going to bypass that, and I think you guys are good. We can skip a couple of missions here. So next one I want to show you is this forth and back. So here we're going to use a block to control what happens in the code. Meet the wait for block. We're going to use this to control the flow of the program, and let's see how. So here again, we've got our drive block, which is to drive the robot forward. We've added a wait for 2,000 milliseconds, which is equal to 2 seconds. The wait for block will tell the code how long to run the code behind it before moving to the next block. So it's going to take this drive power at 100% forward. It's going to wait for 2 seconds, and then it's going to do this next activity or next block in the code. The wait for block is in milliseconds, so this 1,000 milliseconds is equivalent to 1 second. And this drive block will stop the robot because the power is set to 0. So drive power with a power of 0 will stop the robot. So let's see what happens. We're going to run the simulation here. We drive power forward 100% for 2 seconds, and we stop. So here we've encountered 2 problems. I haven't driven all the way backwards to collect this battery, and then how do I get back here to finish the mission to collect these batteries? solve the first problem, we need to change our wait for to 2.5 seconds. And now we need to drive the robot backwards. And here we can do that several ways. We can set up my drive power to negative 100%. And my code should work perfectly now. I'm actually going to hit the escape here. Or I can change this direction from forward to a backward here. But as I run this, it'll again reset that simulation. Drive forward for 2.5 seconds, collect the batteries, and then drive in reverse. And excellent, I have completed that mission. So again, we've done our second mission. Again, these are novice level missions, beginner missions for the students to go through. And hopefully they're enjoying them at this point and looking forward to kind of moving forward. I'm going to skip a couple here and go into this parking right. So we'll actually make a turn into this mission here. Our objective is to find a parking spot for the robot. We're going to drive forward. We're going to collect these batteries. I do need to be careful here to make sure I don't hit this warning sign. This is going to take away points. So when I get here, I'm going to need to stop. I'm going to need to make a turn and then drive forward and hit my target, which is in between these parked cars. It's asking me to run the simulation. This code is kind of pre-written for us, so we'll need to take a look at it, evaluate it, see what the code does, and then potentially tweak it or modify it here. So I'm driving forward for 3 seconds. I then make a turn, and then I drive forward. And I get in a little accident. So here we need to tweak the code and figure out what we did wrong in order to fix their solution here. So our time we drove straight wasn't long enough. We didn't collect all those batteries. So let's change our value here from 3 seconds to 4 seconds. And then off I go. We'll see what happens now when I run it. Again, I'm going to drive forward for 4 seconds. This block here is my turn block. And then I'm going to drive forward again. And congratulations, I have completed my turn right activity. So this is teaching us, I guess in a previous mission, we did learn how to turn right or make a right point turn. Here we are driving forward. We're using that drive power variables or drive powers to make that turn. And then drive forward again. So here your students should learn how to make this turn, how to use these wait for blocks and create, again, I'm only on mission 7 here, but my code is starting to get pretty substantial. It's more than one line of code. There's additional things in there. So hopefully your students are starting to think like a programmer, think like a step-by-step progress, almost like a kitchen recipe where you need to bake cookies. Number 1, you need to do this. Number 2, you need to do this. Number 3, you need to do this. Get your ingredients, mix them together in a bowl, and eventually you get this end results here or this end code. So again, let me, that was a point turn here in this parking right, which I'm going to reopen. So we learned how to make this point turn using this drive power block. We've lowered the drive power. We're down to 15%. We're doing a forward, and we've added a steering variable. To add this steering variable, it's a matter of clicking this gear and checking the blocks. So here I can add a set steering. I can also add a set duration. So if I wanted to change this duration here, I can pull this wait for out and actually add that wait as part of this steering block here. So again, I've got a duration of 1.75 seconds. I've got a steering variable, and this is a ratio from the left wheel power to the right wheel power. So here, with this set at 100%, they're going exactly opposite each other. So I'm making a pure, I'm showing it with my hands. Can you guys see that? I'm making a pure right-hand turn, pivoting, kind of stopping on a dime and pivoting on that dime rather than making a swerve or a curved turn. So again, as I run this kind of modified version of the code, you'll see again, here's my turn, making that turn on a dime or pivot at 90-degree turn, and then driving forward again. We can also do roundabout turns, which is this mission 10 here. So it talks about steering. It's more than just making a 90-degree turn, making an angular turn. So we can do curved turns. Curving allows your robot to turn while still moving forward, just like driving in a roundabout or rotary. the steering value of 100 makes the robot do point turns, so that again is kind of what we just talked about, or a lower value will make it do a curve. So if this is set for 100, this is going to be a point curve. If this is set for a lower number, it's going to be it's, again, a ratio from the left wheel to the right wheel. So there's more power going to that left wheel, less power going to the right wheel, and you'll see what happens here as I run the simulation. I'm making a very tight turn, and it doesn't quite collect all the batteries and doesn't have that radius that I'm looking for. Kind of making a neat little design there. I got a nice circle, but not the code that we want. So this curve is a little too tight. I can hit next. I can change the steering variable from 20. If I change it to 5, that'll widen the turn. You know, I'm not following the instructions here, but I do kind of want to show you what happens. Sorry, then I run this simulation. With the variable at 10, this is what they're asking for, and this gives me my perfect turn to collect all the batteries. Run the simulation appropriately, and hit the targets, successfully completing this roundabout right turn. Let's go back to the Learning Center and do this roundabout double mission. So here's a roundabout right where we learn about the right-hand turn. Here we'll learn about a left-hand turn, doing a steering variable in a negative direction. And this mission 12 does a double roundabout. Let's take a look at this one. So here we can tweak our steering variables to make a double curve. Again, our objective here is to make 2 curves. The first curve is wider than the second. So here I am going to do this outer loop, this big outer loop here, come back to my starting point and then tighten up, make a smaller loop and eventually hit that target. So I have 2 curves to make. First one's wider than the second. For the wide curve, I need a steering variable of 5. The weight block needs to be adjusted to 21,000. And I can check out tips. If I want a tip, I'm going to just showing me a way to speed up the simulation if I wanted to. But so following instructions, let's see what happens here. Driving my curve, I'm waiting for 21 milliseconds. You can see that timer start to increase here. I now set my drive power at 100% with a forward steering direction, or forward direction with a steering of 0. So what happened? It went in a very straight line. My ratio of left wheel to right wheel was 0. So I need to tighten up this second turn here to make sure it actually follows the correct path. So as I change this, I've got to guess and figure out what this variable should be. So let's make it 10 and rerun the simulation. And we'll see what happens. Here it's now doing my second turn. The steering variable of 10. Looks like I guessed right. And I hit the target. So nice job. Let's go back to that Learning Center. So our first, in our bootcamp mission here, the first, I want to say about 20 missions or so are all about basic navigation. So teaching the students how to drive, the various tips and tricks that they're going to learn along the way before it gets into more coding and more detailed coding. You guys ready to do more detailed, more exciting coding? So I'm going to start off with a wait again mission, this mission 24, which is an introduction to sensors. Let me open up this wait again pack. So on your robot, all right, great. Kind of escaped out of those tips. But our objective here, looking at the simulation, is to drive forward. We're going to wait till before we hit this block here or hit this fence that's shown. We're going to make a right-hand turn. We're going to do it again. We're going to wait till we hit this fence and then make another right-hand turn and hit the target. And we can do this with the code that we've learned along the way with a dead reckoning, using a drive forward, wait in a guessed amount of time, make a right-hand turn, follow the same code, drive forward, and wait for a certain amount of time, make a turn, drive forward. But we can do this in a more, I want to say civilized, but that's probably not the right word, in a more accurate manner, where instead of just guessing at a time, we can use sensors. So robots often have input devices called sensors. Why do robots have sensors? Well, these sensors allow them to see, in quotes, what is around them by measuring a physical quantity such as a distance, a light, a color, or a temperature. The more sensors the robot has, the more information it can gather from its surroundings. This data can be used in the robot's programming. With sensors, the robot knows more and can make more informed decision based on that feedback, based on what's around it, like when to drive forward, when to stop, when to turn, how much to turn, etc. Sometimes we want the robot to continue doing a code or continue doing something specific until a trigger point occurs. For example, drive forward until you see or touch an obstacle. Turn right until you turn exactly 90 degrees. Drive forward as long as you see a white line drawn on the floor. All of this data, touching an object, degrees of a turn, the color of a line on the floor, is data the robot receives from its sensors. In CoderZ, we can see this data in the heads-up display, the HUD, which can be seen by clicking on this icon here on the simulation view. This will, as I open these up, these will show me the states of the various sensors. So the robot does have a wheel encoders that we can see the states of, as well as the touch sensor. Our robot in CoderZ has several sensors. I'm going to zoom in on the actual arm here to kind of take a quicker look at those. Nice. So on the front of the arm, we have this touch sensor, this push button sensor, which can detect walls. It's used for collision. So bumping into an object changes the state of this sensor from false to true. On the back of this robot here, which is this object here, is a gyroscopic sensor that's used for rotation. So it can tell the robot is at a 0-degree angle, it's at a 90-degree angle, it's at a 360-degree angle. On the front is an ultrasonic sensor, which measures the distance. One of these, what I want to call eyeballs, but it sends out a ultrasonic pulse, very similar to a BATS radar, if you guys are familiar with that, or students are learning about that in science class, where it sends out a pulse of radar waves. That pulse hits an object in front of it and then bounces back. And then it measures a distance as to how far away the robot is from that object that it just bounced that ultrasonic sensor over, that sonar over. This sensor here is a light or a color sensor, so this can detect surface colors on the floor as well as a brightness. Right now we're going to get to know the touch sensor, sometimes called this bumper sensor, which is on the front of the robot. It's on the front left side of the robot's front, and it has two values. It has false when it's not pressed and true when the sensor is pressed. This sensor is great for collision detection, as you will see in this mission. So let's see this in action here. Again, in this mission, we want the robot to drive forward until it hits this barrier. I'm going to open up this manual control by manually clicking this icon here. This opens up this navigation manual control window, and I can drive the robot forward using this navigation. I can also do it with the keypad in front of me. So as I drive forward, again, I can see the motor wheel encoders changing. And as I hit this barrier, my touch sensor is now true. So as I back off, it's false, it's not pressed. As I hit it, it's then true. So how would this sensor work in our program? Well, we've got a block for that. It is under sensors. Oh, sorry, it's under control flow. And it is this wait until touch. So here, I can bring this into my code and say wait until touch is true. So I can tell the code to drive forward, wait until touch is true, and then perform another action. So the rest of the program we can figure out from our previous knowledge here. We're gonna drive forward until a touch sensor is pressed. So I'll bring that robot out, drive forward at a speed of 100% in a forward direction. We're gonna wait until this touch sensor is true. And then we are gonna turn right. So we're gonna add another motor block. We're gonna make a right-hand turn. I'm gonna change this drive power from 100 to 15. I am going to add a steering and a duration. Here by clicking on this gear, checking off the set steering, set duration as these fields. Here I can go into data and grab a single digit, just click and drag those, or I can right click on the block and say duplicate. Either way, it'll get me the same block. So add those in there for duration. I'm going to add 1.75 seconds and a steering of 100%, 100 to make our turn. And then I want to drive forward again. So after I make that turn, I can right click and say duplicate. That's going to duplicate my drive power. So here I'm going to make this right hand turn. I'm going to tell it to drive forward. Wait until I've hit the touch sensor again. We will duplicate that, make a right hand turn, and duplicate this, drive forward again. So let's take a look at our code here. Here we're going to drive forward. So I'm gonna start at the starting point. I'm going to drive forward until this touch is true. When this touch is true, I'm going to drive power at 15% for a duration of 1.75 seconds at a steering of 100. So this should be my right-hand turn. And then I'm going to drive forward again at 100% power. So this will be my driving down this line. Here I want to wait until the touch is true. I'm going to make another turn, turning right and driving forward again until I hit this target. Think it'll work? Cross your fingers. Let's run the simulation, see what happens. Here I'm driving forward. I'm waiting till that touch is being changed to true. I was a little too slow opening up the display, but I could see the state of this change here in this heads-up display. Then runs the next code. Woohoo! We have done it, folks. We have used the wait until touch sensor. We have made our program a lot more accurate. And again, students could do this with dead reckoning. It will certainly let them solve the problem. Putting a time value in here. However, if that barrier is moved, if that barrier is closer or further away, their dead reckoning is now going to be inaccurate. So to use this touch sensor, I can reuse this program for any space or any distance between those barriers. Let's go back to the Learning Center. We are doing great. Flying through these missions here, these boot camp missions. Next thing I want to show you guys is smart blocks or smart turns. So I'm going to open up this left turns can be smart turns smart block. What we're going to do here is we are going to be smart enough to make our own smart blocks. Let's give it a try. This is not the first or the introduction to smart blocks. The introduction to smart block is here in mission 20. There's more information on the smart blocks here in mission 21 as well as in mission 25. So this is kind of how they work. An introduction to smart blocks, how to import them into your program, how to create smart blocks, and then this is the start of creating our own. So we don't assume the student is going to know how to do this. We do give them that preliminary knowledge before we have them just dive right into creating smart blocks. But I think you guys are advanced. You guys are ready to create your own smart blocks. You guys are smart enough to make your own smart blocks, so let's give it a shot. So smart blocks, time has come to make our own smart blocks. Many missions, including this one, need left and right turns. So we can use those using smart blocks. If you remember correctly, or remember from that last mission we did that drive forward, we did a wait until touch, we did a right-hand turn. And instead of having to remember those variables for that right-hand turn, I can bring them into a smart block, which is similar to a function. If you guys are familiar with coding, familiar with using Java or using a text-based code, you guys write functions that can be saved and reused in future programs and future aspects of your same program. That's kind of how we're teaching the functionality of functions, if you will, for these students by using smart blocks. So as they create these smart blocks and use these smart blocks, these can now be saved and imported into future missions, into future code. So they can just open up a right turn smart block or a left turn smart block and rerun the smart block rather than have to recreate every aspect of code. So to create a new smart block is this quick animation here. It's hitting this plus sign and then saying new smart block. Giving it a name and then hitting the create button. So here we're going to make this left turn smart block. We're going to hit create. Showing me that animation again, left turn. And now I try. Will do. So here to create a smart block, it's hitting this icon here, hitting plus or new smart block, and giving it a great name. I'm going to call it left turn. Make sure you don't have any spaces or any unforgiving characters in this characters here. The code will not read any spaces. It works exactly like a Java code would. So if your Java code or your written text Java code has a space in it, it's not going to work properly. Our Blockly is going to work the same way. So we do need to make sure it's a valid code that can be read by our compiler. So we can't have any spaces in there. Giving it a name. Here I use what we call camel case by capitalizing the first word in each letter by saying left turn to kind of give it that name. And say create. What's going to happen is it now opens up another tab here. Here I've got my main program and I've got my left turn. So this is my smart block defining this left turn block. And I can write my code in this left turn block. So here I'm going to bring in a motor block. I'm going to set my drive power for 100%. I'm going to add my set steering, set duration. You guys should remember how to do this. We'll duplicate these blocks. Oh, that's the wrong button. Duplicate. There we go. So drive power of, we said 15%. My duration was 1750 and our steering was 100. Now I think I want this to go in a steering of negative 100 or turning in a left direction. A positive 100 made it turn right, so a negative 100 should make it turn left. And then I can go back to the program. So as I want to bring this into the program, now as I've defined or as I created this smart block here, it adds this command, this call left turn, under this smart block menu. As I make more smart blocks, I can then import those into the program, and those will all be listed here underneath this smart block menu command. So here, I want to use a motor. So here for my code, if we want to think about that or kind of look at this, we want our robot to drive forward. We want to wait until touch. We'll wait until it hits the wall. We'll make a left-hand turn, and then we'll drive forward again until we hit that target. So let's do the code for that. Here we're going to drive forward. We will go into control flow, wait until touch is true. I am then going to call a left turn and just make a left turn. The nice thing about these smart blocks is I'm now taking lots of pieces of code and making them into one small piece of code. So I've got a big, a relatively larger size of code here that I'm bringing into a smaller function, a smaller smart block here in the code. And then we'll drive forward again with this block here. So looking at our program, drive forward, wait until touch is true, make a left turn, and then drive forward again. So let's see what happens. There it is, success, round of applause for me. On occasion, we do get these pop-up messages that appear within the CoderZ or software, just kind of asking for the students' feedback. This is a new feature that we've taught them. They've learned how to do or import these smart blocks, use these smart blocks in their codes. What did you think? What did you think? Did you like it? Is it, oh my God, were you sleeping? Add some comments in there. I'm going to say it was okay, and comment feedback for our support team. That Trevor is great. So here again, if I didn't like my solution, if I didn't like the results, I can try again. I can go back to the Learning Center, or I can go to the next activity. So let's do another activity. Let's look at this mission 29, which is turn, turn, turn. It's time to write our very own code. So again, let me escape here. Here, after we do this smart turns, we're duplicating blocks. Here we're making, repeating code, essentially driving forward, duplicating blocks, recopying blocks, using that left turn or right turn smart blocks that we've created to do various patterns. And here we're teaching the students that instead of making this long and drawn out code, there's easier way to do things or smoother ways to write your code rather than, again, that dead reckoning and that long code that's now getting pretty long. You know, if you look at it from, you know, kind of looking at the simulation, we're driving forward, we're turning, we're driving forward, we're turning, we're driving forward, etc. As these simulations get bigger and bigger, as these missions get more and more complex, the student's code is going to be 2 or 3 pages long, or could be 2 or 3 pages long. You know, the more dead reckoning they use, the less advanced coding that they use, the more advanced features they use, the more advanced coding. The coding is going to be more efficient and smaller for the students. So let's do this turn, turn, turn mission here. The concept is to write our own code, use all that I learned, or ask my friend for help. So we do want students to communicate. We do want them to use each other as a resource. If students struggle, have you know, make one a mentor for the classroom. And have them help the other students. You know, that camaraderie aspect is a great thing to see in the classroom. So again, here is our mission. We are going to drive forward. We're going to wait until touch. We're going to make a right-hand turn, repeat, 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 do this over and over again. So ever wanted to do something again and again? And in this mission, for example, the robot must drive forward until it hits a barrier. Then it's going to turn right. And then we're doing the same command over and over again. We're using a repetitive and identical drive forward and turn right commands over and over. What if I told you there was an easier way to write this code? There is. It's called a repeat loop, and it makes code much more efficient. It can be found under this control flow menu here. This repeat times. The block comes with the default. This repeat loop will do exactly what the name says. It repeats whatever code is written inside of this block, however many times you want to do it. The block comes with a default repeat value of 1, but of course we can go through and change this number. So whatever blocks we put inside this repeat loop's arms, inside the arms of this block, is next to the do statement, will be repeated as many times as the number I've decided up here. So looking at this code, pop quiz, everyone, hoping you're paying attention. How many times would you need to repeat this drive forward, turn right code? We would drive forward, turn right, wait until touch, drive forward, turn right, wait until touch, drive forward, turn right, wait until touch, etc. So drive forward, turn right once, drive forward, turn right 2, drive forward, turn right 3, drive forward. So we need to repeat it 3 times. I hope you guys had all of that answer, had that answer already prepared for you. So here's what our code is going to look like. I'm gonna program start. I'm gonna click on my repeat loop. We're gonna change this value from 1 to 3 times. So we're gonna repeat whatever's in here 3 times. I'm gonna bring a motor block in, drive forward at 100% power. I'm gonna bring this wait until touch is true. We're gonna wait until our touch sensor is hit, and then we're gonna turn right. Here, if I had a turn right smart block, I could bring that in, or I could make one. You know, we've got a left turn smart block, so let's make a new smart block for the right-hand turn. To do this, I hope we remember from a few missions ago, we're going to say new smart block. And I'm going to call this right turn and say create. Again, this will put up another tab here, defining my right turn smart block. We'll add a speed and duration, add some blocks in there. Drive power 15, our duration is 1750. You guys all remember that. A steering of 100. So that is our smart block there, code here. I can now click and drag, bring this in. Does anybody know why we only see our call right turn smart block here when we don't see the call left turn that we created? That's right. I think I heard it from somebody in the audience that it is not imported yet. So if I go here, I can click on left to turn. That's the smart block that I've already created, and say import. As I import that, that now brings this into the code, and I have 2 smart blocks here. I have a left turn and a right turn. So now as I go to this, I now have both in here. So now they're both imported into the code. They're both available for me to use. I don't need that left turn. I just need this right turn. So here I'm going to wait until touch. I'm going to call right hand turn. So I'm going to repeat this 3 times. let's run this code, see what happens. You guys think it'll work? What do you think? Let's take a look and see. Again, repeat 3 times, drive forward, wait until this touch changes to true. I can see that in my heads-up display here. Changes to true. All right, so what happened? Our code stopped. It ran it 3 times and stopped. We never actually drove forward and hit our target. So what do we need to do? We need to add a drive block. For this drive block, I need to make sure that I place this drive block outside the repeat loop. I don't want this to repeat as part of this repeat sequence. I don't want it to be repeated 3 times, do I? I want this to be separate. So I'm going to click and drag this outside of the block. So it's super important to remember to do that, to put it outside of the block so it's only executed once. So it's going to repeat this loop here, this repeat 3 times. So it's going to do this 3 times. After it's done, it's going to jump down to this next line of code. And then let's take a look. Let's see what happens. Let's cross our fingers, put some magic pixie dust on our laptop screens. I'll open up the touch sensor here in the heads-up display so you guys can see that. Excellent. I have completed the mission. Well done, Trevor. Well done. I hear you guys all applauding. Thank you. So that's our repeat loop. So again, that's another way to use code to minimize the lines of code, to make it a lot smaller and a lot more efficient with A, smart blocks, and B, that repeat loop to repeat the same code over and over again. So a lot of these next missions here, the 30 through 40 or so, or 39 here, do use this repeat loop. We're making zigzag patterns, various patterns, collecting points along the way here in these loops. Kind of again using that process. And then we get into our last set of missions here in Bootcamp is to meet the gyro sensor. The gyro sensor is that sensor on the back of the robot, which allows you to determine an angle. This is great. It's a great feature to use. So instead of us having to guess at that dead reckoning, if you remember, I had to memorize that speed of 15, the duration of 1750, 1.75 milliseconds, and a steering variable of 100 to do a turn. Here, I can use this gyro sensor on the back and say goodbye to those time-based turns. Time-based turns are for newbies. The gyroscopic sensor detects how many degrees the robot turns. It just turns slowly or you might overshoot it. So if you're turning on a very fast, kind of pivoting and rotating quickly, the accuracy of the gyro sensor drops down quite a bit. So here, let's take a look at our code here. I'm got a drive power of 100, driving forward, a steering of -100. So this is a very fast turn a very fast pivot turn that I'm looking at. I'm going to wait until the gyro is at an angle of a little greater than or equal to 90 degrees. And then it's going to do these commands here. So here it's going to stop and then drive forward. So it's going to stop its turn and drive forward. So let's see what happens. And we can see, okay, we've turned way too fast. Our turn rotated, we told it to stop at 90 degrees, but our turn went way further than 90 degrees just because of kind of real life situations or real life variables that would happen in real life. Say, for example, if you did have an EV3 robot that you're using, that you placed on the floor, if you try to make this exact same turn with that robot, there's no way it's going to turn at that fast speed. And we try to replicate our simulation by adding these variables that you would see in real life. So as the students get further in or progress further into the curriculum, or I want to say curriculum, into the missions, we add what we call dead reckoning, which is internal variables that make the dead reckoning, the time-based solutions, less and less accurate. So for example, with a real robot, your battery voltage isn't going to be the same. You may plug it in, you may charge it. It may be 12 volts initially when you first start your mission, but after 20 minutes, after 30 minutes, that voltage is going to drop down to 10 or 8 volts, and your robot performance, or robot isn't going to be performing the same because of that lower battery voltage. Or for example, you can't take a robot and place it, pick it up and place it down on the ground at exactly the same point every single time. I mean, you could probably put witness marks on the ground and make lines there, but just from your hands placing it on the ground, there's no way you can get it at 100% exactly at that same point every single time. As well as friction variables. In the real world, there's friction of the wheels against the floor, the rubber against another surface, whether it's carpet, whether it's tile. Those friction variables make your robot perform differently. So again, we incorporate those here into the CoderZ software to make the robot simulation more realistic. The variables are not exaggerated. They're very minimal at the beginning, and then as students progress through, they get more and more advanced and more exaggerated for the dead reckoning problems to be more substantial. So we want the students to use sensors. We want them to use touch sensors. We want them to use a gyro sensor. We want them to use an ultrasonic sensor to make their code accurate and consistent every single time. Where you may see if a student is using that dead reckoning, their code is going to be inconsistent. It may work one time and not work the second time. It may work, it may work 2 times and then not work a 3rd time. It's because of those dead reckoning variables we incorporate, and we want them to use sensors into their program. So try doing a slower turn. Got it. So instead of this being at 100%, let's make it 10%. Do a very slow turn. We're going to go forward, steering at 100, and then we will rerun this simulation here and see what happens. Here's my turn. I should have put on this heads-up display here where I can show the variable of this gyro here. But you can see that turn went exactly 90 degrees. With this set at with the drive power set at 100%, it turns way faster, way further than 90 degrees. It goes to 94 or 95. That's why we don't see a straight line with a drive power slower. We'll see this gyro turn at very slow speed. It's waiting for that to be 90 and then runs the next line of code. And our robot does follow the line pretty closely. We're not perfectly accurate. I could probably slow this down to get a better result, but it does solve the mission. So nice job, Trevor. And that's our gyro sensor. Let's go back to the Learning Center. So, and that is the 44 missions of Bootcamp in a quick nutshell. Hope you guys enjoyed that. I'm not going to give you guys all the solutions. We want your students to go through a lot of those. We want your students to go solve a lot of those missions, or solve those missions on their own. And so this is just the bootcamp stage. This unlocks on October 15th to the students. So those are the missions that they will see. You guys got a sneak peek of that, of some of the missions. You guys got some of the solutions to the code. So I hope you guys remember that, or at least can rewatch the webinar. You can actually rewatch the webinar with your students if you want, and show them the code. But again, that solves quite a few of those bootcamp missions, gives your students a basic training on how to write their code. So after bootcamp ends, we transition into the competition stage, which does get a lot more harder, a lot more complex. We add more dead reckoning features. We add more advanced coding. We do use that ultrasonic sensor. We do use that line follower, the color sensor, to detect lines on the floor and do more advanced coding features in there. So I hope you enjoyed that. Let me get it back to Graham. We'll start to answer the questions that kind of popped up here in the chat field, and talk to you then. So thanks for your time. Bye.
Okay, thank you, Trevor. That was great. Should I put a picture up?
Sure.
We're here. Okay, there's the link, gocoderz.com. Bootcamp starts, so we'll turn that on probably pretty early in the morning, and you should be able to log in. We will start sharing information about the leaderboard links, and so you'll be able to see those. They'll be empty, of course, until schools start participating and start racking up points. But now's the time to get your students invited, get them online, and get them logged in. And any problems that you have, these are the contact numbers. And once again, this set of slides will be up on the the website, so you will be able to find all this information, and we will answer any questions if you send them into the emails, and we will get back to you as soon as possible. For those of you that do have time and want to hang around, we're going to just look at some of these questions and see if there's anything that we will mention. A couple of people asked about the window for the school finals, and the answer is it is a window. It is for the whole school, and it is 2 hours. So this will start sometime in. It gives you a bunch of time to find that window that can work for all the classes that are participating. But we focused on trying to create that school spirit, get everyone involved, and so you do have to find that 2-hour window that everyone can participate, whatever class they're in, and hopefully that won't be too much of an issue for all the schools.
Yeah, the great thing about that is students don't have to be in a single classroom to do that. You can use multiple classrooms. Students can compete from the library. They can compete in that finals from pretty much anywhere that is within that window, but it does have to be one specific 2-hour window in that 2-week block that we schedule.
There were also a couple of questions around scoring and what happens if students skip specific missions, maybe because they participated last year, maybe because they find them too simple. So let's clarify this. In the boot camp, this is the learning phase. The more people that participate, the more people that are involved, the better, but the scoring doesn't carry over. So in boot camp, if you skip missions or do not finish missions, it doesn't make any difference. Once the competition phase starts, and then for the qualifiers phase, every mission counts. So completing the missions, doing as many missions as possible is important. The more that you do, the better your school score will be. And so it's important to get students to do as many missions, not skip missions, and to finish as many missions as possible to boost the score for the entire school. There was a question once again about the students under the age of 13. The platform is COPA and FERPA compliant, and so any student under the age of 13 will get an automatic message where they have to provide their parent information so that we can get the parent to approve their participation. At that point, they will be allowed to join the competition, but as an anonymous participant, and only after their parents provide the permission will they have full access, or will they show up on the list and on the leaderboard. Somebody else said they hadn't got their org admin information. If you're registered, signed up, paid, or have sent in a purchase order and you haven't received your org admin information, check your spam filter or get in contact with Trevor. Something's wrong. You should have received it if you have completed the registration process. There were a lot of technical questions about the different sensors. I'm not going to go into that detail right now. The sensors operate obviously each one a little differently based on their functionality. Touch sensor, color sensor, ultrasonic sensor, and gyro sensor. Each one operates a little bit differently. If we need more detail about that, you will find that there are tutorials that you can click through from the help menu. You can find little videos there that explain them in more detail than Trevor went into today. So if you want to get in there and look for more detail, please poke around with the help screens and you'll find everything you need. And the final question that came in at the end was what age groups are able to participate, and this is for middle school. So the competition CRCC is designed for middle school age groups, although in the CoderZ platform itself, we have some elementary school and we have a number of high schools. We expect that in the competition itself, this is focused at middle school, and middle schools will be invited to the finals. With that, I think we're done, and this has been great fun spending the last weeks with all of you. It's been successful.
I'm really impressed with the participation levels here in the webinars. We've had a good number of people show up for these webinars, very attentive. Great questions that we're receiving as well. So we appreciate you guys taking time out of your busy day to spend that hour with us, or a little over an hour in today's case. But thank you for doing that. I appreciate it.
We're really excited.
May the code be with you.
Go CoderZ.